Okay, thank you to be here for the lecture of today. Let me restart quickly from the definition of the injectivity. You remember last time, before last time, let me say, during the last lecture, I applied this the theorem, let me say, to judge the object, the injectivity of a system, or let me say, in this case, we are speaking about a transformation. Um, look at the definition. I already presented this. No, it's the lecture which we considered, I don't remember when. A definition of injectivity is here, in which we consider, if we consider the linear transformation, again, we speak about injectivity also in terms of system, but let me remain on our topic. A transformation, linear transformation T from V to W, we will see more in depth now the meaning of V of W today, is said injective, or we say is injective, if inside the definition means if and only if. T of x equals T of y implies that x equal y. X and y belong to the domain again. V is the domain, W is the image. We will see what I intend. In general, we can say codomain, but we have a difference between image and codomain. But of course, we can define, probably in my opinion, more effectively in a contrapositive definition, in which if x is not equal y, T of x is not equal to y. Let me show you graphically what is the meaning. Is I don't know if this definition recall already something. I show you a graphical interpretation so it's clear, because very often in our cognitive capacity, graphically we understand better than this language. It seems to be abstract, no? Because nevertheless sometimes it is necessary to image. By image means build something. Now I build for you. 1 second. I need just 1 second to look. I have it directly here. So I can repeat for you. Some fundamental definitions which can help for the next. Oh, I have something better here. I don't have. Doesn't matter here. Let me see what this. Let me switch on the lateral camera. Oh, it doesn't work. Now. Huh? Oh, now vielleicht? Now probably. These techniques. Oh, weird. Now, okay. No. Okay, probably now. Okay. Look at this picture. Let me switch. Now, look at this picture. Here we have a graphical representation of a function. What is a function? Or transformation. For us, in our course, function transformation, we are using a synonym. We can see that just one element have a correspondence. I mean, x1, 2x1 correspond to y1, 2x2 correspond to y2, could be also not necessarily y2, could be also y1, 100, but just one. I mean, in order to understand better, if x1 to x1 correspond to two values, we are not speaking about the transformation of function. If x1, we have two elements in y, for instance, y1 and y100, we say that this is not a function, because the function is characterized by the unique correspondence. To x1 corresponds to something, but just one. To x2 corresponds to something. It doesn't matter how I call this, but just one. This is for practical reasons. For practical reasons. Because, for instance, consider the mark of our examination. You see it in the data sheet that to your name corresponds 2 marks. You have a 1,0, you're happy, and somehow you read again your name with 5,0. Of course, it's unclear what is your mark. Clear? You have the data sheet with the name. Now, your name appeared twice, but again with your matricle number. I mean, of course, where are you? What happened? We cannot manage such a situation because it's 1,0 or 5,0. This is for practical reason, because also this stupid example creates a problem. Because if I put 5,0, you come to say, I have 1,0. Just, excuse me, this trivialization, just to understand why the definition of a function here is, of course, is just as a flesh out. It's something in which we consider just one element in the codomain. About X domain and Y codomain, I already told you. We will see now the difference between codomain and image. Sometimes they correspond. Sometimes also, roughly speaking, we are considering synonym, but they are not the same. Codomain means corresponding domain. Now we can understand also the language. The language math is important. Therefore, at the beginning, I introduced moral, amoral, immoral. It's important. It's in a way to think mathematically. We associate in the language. I mean, we have a domain. Domain. You know the root of the word domain. Domain. Doma. What is doma? House. We live in a house. Codomain, a corresponding house. Could be so interpreted. Doma is domestic. Auf Deutsch kann man sagen domestic. Nein, wisst ihr nicht? Aber warum versteht du? Auf Englisch. Yeah, domestic. But the root is doma, house, close to house, domestic flight. This means no international flight, something like that. Domestic animals, cats, dogs, no? Domestic animals, you understand that? We are domesticated. I try to domesticate you in math. It's not socialized, but just to laugh. It's clear what a function is. But I already told you. In any case, look now a little bit what in this case we have. We don't have a function. Exactly the stupid example about the mark. You got in the sheet 2 marks with the same examination. Of course, we cannot work with this. We have a problem. We have a trouble. Just close with this. Look now about the injectivity, in order to understand exactly what I told you before. You remember x1 not equal x2, in our definition was x not equal y. No? I had the notation is different, excuse me, but we can understand. This is x, this is y. Two different values, two different students, but they can have the same mark. The correspondence works. I don't have trouble. If both you have 1,0. In many cases, we don't think about the function. 1,0 is 1,0. But in order to understand, two students could have the same mark. This is a correspondence with which we can work. Because it's not that anybody take 1,0. Normal is not that good. We can work with this. But if you have two marks, you come to me, what is the correct? It could be that I cannot answer probably in the administration. In the administration, they make mistakes in this transformation, this operation, which isn't a correspondence between your work and the mark which I try to draw. This, of course, is a function. This is, of course, a function because it does not contradict the definition. Because to this element, we have just one element. To this element, we have just one element. This means isn't a function, yes, but isn't a particular function because this is not injective function. Isn't a problem? Not injective. Because we have two different elements, but just one corresponding. It's a particular function. Isn't a problem? No. At least it's not a problem. I mean, we can work with this. Of course, we have some limitation. Clear? Now, quickly, because I don't have much time, I try a little bit to clarify what happens in this picture here. We have X domain, Y codomain, and this is written here that read here that this function is not surjective. Interesting. No? And then I try with words, probably having a better material to show you. If you give me some minutes, I will try to find. But intuitively, we can understand that we can see here in the codomain two elements which is there, but they don't have a corresponding X. This is the concept of surjectivity. This means that the codomain Y is not totally covered. I give just an intuitive, then we will go in depth an intuitive interpretation. When my correspondence does not cover the whole codomain, in the first page I put Y equal codomain, means the element of my set. With this representation, we have two sets of data, X and Y. This is difficult. What is the feeling? It's difficult to understand. Okay. Now we will do more calculation, more exam exercise. Now, concept. Because math, it's a shame. We need calculations, but it's not a calculation. The kernel of the math, the way to think, believe me, moralish, amoral, this is math. Meaning, believe me, I was not good at math. It's real. If math is 1 + 1, this is totally wrong. Then I understood that thanks to some very good teachers, much later, that math is not this, also this, but not all. Okay, this means if, let me roughly speaking, so the codomain is not totally covered by the transformation, we are speaking, let me roughly without a formal definition. Then we will go in depth in the formal definitions or something similar. We are speaking about that the transformation is not surjective. If I cover all elements of the codomain, we say the surjective. And in this context, now I can clarify the difference between image and codomain. The image is represented by the set y1 and y2, because it's the subset. About subset, I told you, no, it's intuitive. Subset in German is Unterräumen, no? Unterset become subset in a part of the set. In a part of the set. Is the part of the set which is covered by the transformation. Image, because like in projector, I doing a projection of my domain into a part of the codomain. We say image. It seems to be difficult to remember, but it's intuitive. If you do some exercise, we will do exam exercise, it will be easy. Image is a part of the codomain. Which part? The part which is covered by the transformation. Let me see, roughly speaking, so we can see here. Yeah, I have a better material somewhere, let me see. But I tell you in the meantime. Now, we define an invertible transformation, very important sometimes in some application, if the transformation is injective and surjective, must have both properties. Of course, the surjectivity is not so extremely relevant, but nevertheless at an meaning, because we can restrict to the image the possibility to invert the transformation. Let me show you probably something better here. 1 second, and I come back. And then we will do something directly to the exam exercise. No? Also, last time we calculated or we answered the question if the transformation is injective or not using a theorem which I will repeat now. We wait a second. It is difficult, but you have already seen this, I think. Did you see? Of course. Injective, surjective, invertible. Not really. Okay, it's good. Because we are here to learn something new, otherwise. In the meantime, I introduce again, here is a little bit more in depth, It's important to analyze this transformation because very often we need in advanced mathematics, in application of mathematics, we need the invertibility of the transformation. This means the transformation should be used in both directions. Student marks students. Then the example probably is not it's not exactly what I want to say because I don't know if you can use this. But in many control applications, in many data science applications, to have it, let me say, in a correspondence between a set to another and vice versa, can help in the application. Again, the invertibility of a transform is related to these two properties. To invert the transform, this means to work from here to here, could be useful. The transformation must be invertible. An example. We have some in a physical system, we have 1, 2, 3 causes, and we have 1, 2, 3 effects. And then we want to reconstruct the causes starting from the effect. This is possible if the transformation is injective and surjective. Look, this transformation here is the function, first of all. Secondly, is injective, we can see, and is also surjective because no elements are free from the transformation. This means I can reconstruct the phenomenon, the causes, I can reconstruct what happens starting from the effect. This is the meaning why we use an inverse transformation, to reconstruct the input from the output. But this is possible just if the transformation is surjective and injective. Question: is this transformation, first of all, is it a function? Loud, loud. Is it a function?
No. No.
Du glaubst. Do you believe this is a function? It's a function, no? Because we have just one element in the codomain corresponding to each component of the domain. Each component. Please attention. Each, 1, 2, 3. We have just one. Is it injective? Loud. Is it injective? This could be the question in the exam. Please graph an injective transformation using sets. This is the question. And we have the answer here. I don't show the answer. Is it injective or not? Why is it so difficult? Try it. It doesn't matter if you make wrong. We have a 50% chance. I realize that it's unclear what injective is.
I would say it's not injective.
It's not injective because you have two different elements. Look at the definition, the mathematical definition, x not equal y, to distinct. You understand distinct? Yeah, how was would say in German, distinct, verschieden. But we have the same image. I use the word, the same element in the codomain. Not injective. This means, please pay attention now, not invertible. Because if I am here, you have two elements. It's unclear. The direct case of the two different marks for a student. This cannot be inverted. If this is the physical phenomena, please pay attention, which I measure, and this is the transformation which I have in physics, I cannot say if I am here, if happens because this, or if W3 happens because this. Both is possible. If both is possible, we say that the system, or the transformation in this case, please pay attention, is not observable. I cannot say that this effect came from this or came from both. Now it's more clear why we are analyzing this property. In physics, in many applications, also in economics, very often we need to recognize if something happens, what is the cause? Look at this. Question, exam question. Is the function, first of all, isn't a function? Isn't a transformation? Isn't a map? Yeah, it is. It is. Each element are mapped, and each element having, let me say, just one. Just one. This is the concept. Question. This isn't a function. And then we can pose other question. If it's not a function, it's ready. We cannot answer. We cannot work. It's injective. Different opinions about that. Everybody agrees it's injective. No, it's not injective. You're here a little bit too relaxed. It's not injective. Why that? Because we have two different elements, but two different elements correspond to just one. I will insist a little bit because this is important, believe me. I mean, I don't know if in your life you will work with economic mathematics or mathematics in an economy, but believe me, conceptually must be understood. It's not injective. Question, is surjective? Isn't a function. This means allow me to ask more. If it's not a function already, I don't ask anything. Is an surjective transformation, in your opinion, and this is very in your opinion, it never tells an opinion. Please pay attention. Why is it an opinion? Because it's based on a definition. But given the definition, then I don't want to use the word opinion to be precise. But I use this word in order to relax. This could be the question for the exam. Draw more actively, a graph, non-surjective transformation. This is not subjective. Why that? Because we have W3, which is not covered by the transformation. This is the concept. We have also a more formal definition, but this is, I would like to fix easier the concept because if you read the definition, we will see a little bit later. Is it invertible? No. First of all, because we have this not injectivity, because from here I cannot correspond just one element, and not all element have a correspondence. Remember, each in this we did in geometry. Let me see the last one, and then we'll go ahead. Is this in a function? Is this in a function? Yes, it is. Is this injective?
Yeah.
It is. Very good. Is surjective? I indicate something. Is surjective?
It's not covered.
Is not clever. Cover is not subjective.
Not fixed.
This means is not subjective. Is invertible? No, because to be invertible must be surjective, is injective. Reason. Because this element doesn't have any correspondence here. If I invert, I need that each element have one and just one corresponding element. Therefore, I need the injectivity, I need the surjectivity. Here, the injectivity is guaranteed, but it's not guaranteed the surjectivity. Nevertheless, I can reduce this set here to its image. In this case, I can invert the image. It's written here, look. To sum up everything, the codomain consists of W1, W2, W3, W4. This is the codomain of the function, or the transformation. But the image, in some books you can find range, which is not necessarily the codomain, consists of just three elements. The element which have a correspondence or any correspondence in X. Y1 at this one, Y2 at this one, and Y3 at this one. I don't know if now is clear the difference between image or range in some books, the same and synonymous, and the codomain. At the end, if the codomain is not equals the image, the transformation is always not surjective. Now we go ahead a little bit more practically, and then we can understand, I hope, a little bit better. I hope a little bit better. It's a little bit very important that this new concept. We are here to learn something new. The goal is not directly to learn, but to do exercise with our cognitive capability. Because it could be that if you are not in the field of economics or mathematics in economics, it's clear that probably you don't use this. But we are here for the education, to do exercise. Therefore, it's important basic knowledge in math, also in master. But very interesting, I would like to inform you when we hold this seminar in mathematics psychology, in order to understand how the mathematics is important, and also in fields that it seems to be uncommensurable, not measurable, feeling. What is in German feeling? It's not mood, you know? Feeling, the feel. Mood is still mood, no? Zulala, okay, I insist, because this is important for the. Let me see what I have here. Look. In European. Oh, no, don't read. In European, this function here is injective, subjective. Y equals x squared. No, this we know from Gymnasium. Is injective, subjective, or what is this function? Look, two different elements, one element correspond to this. It's clear that this is the domain, that I try to apply this more set-oriented language in this XY is for Gymnasium, you know? In more practical, I would like to say, you know, like we have here something we change and the corresponding Y. I don't want to put example, but you have for Gymnasium everywhere. We have two different elements on the domain X, and we have just one element in the codomain Y. Is the function injective or not? What is the meaning here? You understand or you say yes? It's not injective. You got two elements, twice. You have two different, but not two different elements in the codomain. What about an injective function? For instance, the line. Excuse me, that's normal. Yeah. I try to put good mood, but I'm not sure if I am able to do. I ask you, injective or not?
No.
Because you heard them. Okay. No, I try to explain. There are two different elements in the domain X, just one corresponding element in Y. Now it's clear, no? But it's really difficult. No, that's easy. Second question. Is the transformation so represented in this form, in XY Cartesian form, but is equivalent to what I told you before in set form, or something which can be, I would like to say, see the reflection. Is surjective in your opinion? Don't read. The solution was there. Yes or the nine? Yes or the nine? Yes or the nine? Yes or the no? It is difficult to see, in your opinion. It's not subjective because the codomain, the y-axis, and we cover just the positive y-axis. This means just a part of the codomain. But anyway, it's not so. I understand that the first time, yeah, it is written here. I will scan, I will upload. Okay, let me now go more time. We will see that at the end, you will say that is easy. Here. Look now at this theorem, which you already applied when we did the exam exercise before last time. I don't remember when exactly. Let me share now Ah, 1 second. Again, the lecture number 9. If I remember well, let me share. At the end of this exam exercise, no, was not here. Ah, yeah, the theorem is here. Look at the theorem. This is written that in a linear transformation T is injective if and only if the kernel of T is the trivial one. You remember we applied this. We applied this. Please pay attention, nevertheless. At this concept here. It's a little bit difficult, but we will go in depth on this. If the dimension of V equals the dimension of W, keep in mind, I will clarify. Let me see if I can go in depth a little bit. I can tell you now, but it should be nice if I find the sentence. Do you remember the nullity theorem? If I find, you remember the dimension of V, the dimension of the domain, equals the dimension of the kernel plus the dimension of the image. I don't know if you remember this. Should I find it? What we discussed this? Let me see. I thought it was here, but it's not. Let me see. Sometimes it's here. This is lecture 9, excuse me. Yeah. One second. I'm looking for the material. Why it's not I cannot open. Don't understand. Now. Really, I cannot understand why I cannot open. Now. Let me see if I find here this. Yeah, okay. Let me switch now. I can clarify in a few minutes. Let me switch here in this last lecture on the topic of linear algebra. And then we will see some exam exercise. I will go in depth on this dimension of V equal dimension of W. And we will try to to go in depth on this surjectivity, injectivity, and so on. Look, we have a transformation from V to W. Linear transformation, yeah, is said to be surjective. Sometimes surjective, some books is onto, but surjective. If for every element W of the codomain, there exists at least an element V of the domain which TV, T of V, better to say, equal W, is exactly what I told you. All elements of the codomain must be covered. Keep in mind this picture. If something is not covered, it's not surjective. It's written in a more complicated form in this sentence here. But the last sentence here, this remark, we already discussed. Because as I told you, if the range or image, I like better image, right? Yeah, equals the dimension of the codomain, this means it's surjective because I cover everything, the image, the projection, cover everything. It could be also considered a definition. This is just an annotation. Look at this theorem. Say, if the linear system is surjective, then dimension of V large or equal dimension of W. Think about a little bit later, it's a shame, but think about, in order to interpret this, how possible to interpret it. It's not so difficult, because if the dimension of W is larger than the dimension of V, there is something which is not covered intuitively. I don't know if it's clear what I intend. If W must be covered, think about the idea. W must be covered totally. This means if the dimension of W is larger than the dimension of V, intuitively cannot be covered totally. Just too intuitively. Is a necessary condition that we can see because it's if. This means that if it says if LT is not surjective, but I cannot say when it's surjective. If it's surjective, we have this one. But don't say if it's not surjective. About this, I already told you that must be injective and surjective. Yeah, just recall I told you before. If the kernel is just the trivial element, otherwise I cannot say that it's injective. Very strong, no? If and only if. No? I can say if it's surjective, I can say if it's not surjective. Invertible must be both, no? Injective and surjective. I clarify a lot about it. Let me see if I can add here something. Let me skip a little bit. Probably it's better. I will tell you until here, and then we do some exercise. Yeah, look here. Let me go ahead with this slide here. Now, do you remember here? It's times, no? K times A matrix with dimension A, M times N. It's not K. I'm sure they have a better presentation with the LaTeX problem. No? M times N. This means M row, N column. No? It's written here. but this is not K, but times. It's an LaTeX error. We rank K. It is not this K here. This is times. Do you remember I told you about the rank? The rank of a matrix is the maximal number of column, as written here, or row, which are independent. Now, theorem. In a matrix with m row and n column, the rank of the row equals the rank of the column. This must be keep in mind, but in any case, try to remember. Look at this, and then we will do exercise. Properties. M is the number of independent rows. If M is the number of independent row, we say that the dimension of the image of range is M. N is the number, if N is the number of independent column, we say that this is the dimension of the domain. Why I'm speaking about the matrix now? I'm speaking about the matrix because, as I told you, we have an exact correspondence between transformation and matrix. Look, very important these properties. M number of row is the dimension of the codomain. Nothing to do with the relative connected with the image. The number of row, not the independent number of row. The number of row is the dimension of the codomain, the number of row of the matrix. The number of columns, just the number of columns, not independent columns, is the dimension of the domain, which equals the dimension of the image plus the dimension of the null or kernel. This is the nullity theorem. You remember, I tried to interpret the nullity theory. The dimension of V, domain, equals the dimension of kernel plus the dimension of the image. This means what I have in the domain is transformed in the image or in the kernel. If the kernel is 0, in this case, we have an let me say, an injective transformation, because, let me say, roughly speaking, I don't annihilate in a subspace, because 0 is transformed in 0, but not other elements. This means we have a necessarily, I didn't do mathematical demonstration, an injective transform, because we map without, let me say, losing dimension of the transformation. Let me conclude. This is again to recall what I told you now. The dimension of the kernel of the transformation plus the dimension of its image equals the dimension of the domain. Okay, we are almost ready. Let me conclude directly with this sentence here. Probably, yeah. I need just this slide. But this is exactly what I told you. The injectivity is connected with the dimension of the kernel. If the dimension is the kernel, we have the injectivity. If the injectivity dimension of the kernel is 0. Concluding with this, and then we do an exam exercise. Then we take a rest a little bit. I have a matrix which reflects the transformation. We say it as is injective. Is injective if it's only if. Look, n less or equal m. Is surjective. Then we will apply together if n larger or equal m. N, if you remember, is the number of row, column, excuse me, column. M is the number of row. we say in this case here that we are in the presence of full column rank matrix. Here we say that is full row rank. It's easy to do the exercise. No? Look at this. Exam exercise. Look at this matrix here. This is the solution here, but let me show you. What about the rank of this matrix? It's a matrix which consists of 2 rows and 3 columns, right? First question. Don't read the slide. What is the dimension of the domain, in your opinion? What is the dimension of the domain? We multiply this row, multiplying a column, no? Which column is x, y, z. The dimension of the domain is 3. Because each vector characterized by x, y, z is transformed into something with dimension. It depends. At least apparently, we have x, y, z. X, y, z is transformed into something, right? X, y, z, because of 3 columns. It transforming apparently in codomain with dimension 2. I don't know if it's clear what I intend. X, y, z is transformed. Should I do the calculation to understand a little bit better? Yeah? Okay. I don't have it. I forgot to bring something to write. We have a piece of paper which I can write. No, yeah. Yeah, perfect. Let me copy and then we will move to the lateral camera. Okay, it's good exercise. We do this exercise that we take a rest and we will come back with other exercise on this topic here because it seems to be not easy. No? Meaning, I have to switch, no? Clearly. This is the matrix. You remember we learned that the matrix represents or can represent the transformation. Matrix transformation, basically they're the same, or can be considered the same in the context of a correspondence, in the context of linear transformation, transformation. Why not? Excuse me if I repeat always the same words, but if I speak about transformation, I can equivalently speak about matrix, in which we can see a domain and codomain. Please pay attention to what I'm saying. Considering its column and its row. Now it's clear. We did at the beginning of January when we came back. Now is probably a little bit far away. Let me more concretely show you what I want to show. 1 second. Apparently, it seems excuse me, set. Let me see, in vertical probably is a little bit better. You remember the concept seems to be something like that. No? Why that? Now a little bit abstract, but I will be more concrete. Um, you remember this? Multiply. Eh? I transform x, y, z into this one and into this one. If you read, if I apply this matrix to x, y, z, this was the idea. I don't want to repeat it, but to try to write the transformation in terms of a matrix. No? Row multiply possible column which define the domain R up to 3 because we have 3 variables. No? X, think a gymnasium. X, Y, Z. No? Dimension 3. This makes sense a little bit. No? Is transformed into dimension 2. Do you remember last time we insisted on this with A, B, C? Last time we did the exercise in different form. I gave points, and then we construct the transformation into the matrix. Now I give, but I gave also this one, I think, once. Now I am giving the matrix, I have the transformation. I mean, what is the meaning? Let me write in horizontal, probably is better, I don't know. I hope no mistakes to copy, no? This means this, this, this element in the room, 3 dimension, is transformed in a plane, 2 dimension, with this law. This means this matrix in the context of a possible interpretation in terms of transformation. It's not clear. No? I will be more explicit, but please pay attention. It's a shame that this topic is not clear, but I do my best. We have time to understand. If we don't have much time, we will reduce the differential equation. Probably you know the differential equation from Math 1 and Math 2. You don't know. You don't have Math 1, Math 2, no? Yeah, this is also the meaning to be here to learn math because we know I knew that not all students have math 1, math 2. Therefore, the indication if I have time to do also a little bit the differential equation, a little bit. But this is more important in practical meaning, even though it could be that the practical meaning in this course is not clear. But believe me, I apply this concept. Okay, let me do more practice. Um, let me, I don't know if this could help to understand more practical. Again, what I wrote before. if you want to, I can call this with another name, I can call this with, but it's fixed by this transformation. Because I apply this matrix to a possible domain characterized by x, y, z, because x, y, z is the domain which can be the unique domain in terms of dimension, which can be seen applied to this matrix because we have 3 columns, 1, 2, 3. This is the image in accordance to this transformation, first element of the transformation, or first row of the transformation. This is the other element in accordance with the second row. Therefore, not R up to 3 to R up to 2. I apply this transformation to my domain x, y, z. Must be x, y, z, yeah, because I have 3 columns. This means the number of the columns states the dimension of the domain, R up to 3. The number of the row state the dimension of the codomain. Let me write this sentence here. Because I already told you about that in the slide, but probably with too many, too much things together. The number of the column states of the domain. Dot. Then the number of the row state the dimension of the codomain. Right? Until now, because I transformed x, y, z in 2 components. We can call here, I don't know, y1 and y2. Anyway, 2 elements. Let me see which page. Apparently, as I told you, apparently, this is the meaning. Apparently, I will clarify now. Row. In particular, apparently, at the meaning here, because the dimension of the domain is not exactly the number of the column, but the number of independent columns. But apparently it seems to be that I will transform x, y, z, because I have a 3 element, This means formally, yes. Formally, yes. But now we will see something interesting, because really the dimension is characterized, dimension of the domain, what really transform is characterized by the independent number. Now we will go in depth on this. Let me write apparently. Why apparently? You remember? Yeah, I told apparently. It's not wrong to write so. No, at the beginning I see. Now I try to clarify. Let me calculate the kernel of this. You remember we did together last time. Let's calculate the kernel or null, no, of A. Now we do this exam exercise. Very often I do kernel of, excuse me, of A. This means A multiply, how we call here, x, y, yeah, x, y, z must be 0, 0. Remember, I have to calculate x, y, z, which is transformed into 0, 0. This is the kernel, the definition. A set, the kernel is a set of x, y, z, is transformed in 0, 0. This means 1 minus 1, 1 minus 2, 2, 2, into 0, 0. Let me do these calculations. Let me write it. Let me already, I did already know this. X minus y plus z equals 0, minus 2x plus 2y plus 2z equals 0. Is exactly what I wrote many times, not this expression. Now, the difference which I put equals 0 because the definition of a kernel isn't a set to be calculated. In this case, characterized as x, y, z, nevertheless three-dimensional, but apparently I show you a little bit what I intend. This means I copy again here. No? Okay. This means from this equation, x equals y minus z. If I plug in the second equation, I have minus 2, which multiply y minus z plus 2y plus 2z equals 0. This means, if I look here, z equals 0, right? No? Better to be precise is 2z equals 0, no? Which imply z equals 0, which imply x equal y from here. If I plug in z equals 0. This we can see what is the set. This means the null of A is 0, z equals 0, and x equal y. For instance, I can put, it can be written in this form. You remember this? For each x. Think about it a little bit. We can see that the transformation is not injective because the kernel is not just element 0, 0, 0. You remember the dimension of the kernel must be 0. It's not 0 because we have one dimension, this line. I can conclude that the transformation, which corresponds to the matrix, is not injective in accordance with the theory. Okay, let me go ahead. What about now the image? Let me write again the matrix. The matrix was, let me copy, 1 minus 1, 1. And then minus 2, 2, 2. No? This was. I hope I copy correctly from the slide. No? I copy correct. How I can, the dimension of the codomain, the dimension of the codomain is 2. Did you agree? We have 2 rows. We have seen this also in the slide. Let me show you directly. Oh, I don't know where is. Now, what about the dimension of the image? This is the question. I have to look how many independent rows I have. No? This means I can apply so A, which multiply minus 1 minus 1, 1, plus I do formally, no? Minus 2, 2, 2, equal 0, 0, 0. You remember the definition of dependence or independence of vectors, no? I have to, they are independent. They are independent. When I generate 0, 0, 0 in a trivial way. Basically, A equals 0, B equals 0. Now, let me solve. Otherwise, they are dependent. Let me see. From here, I have A equal to B. If I put here, I have 0 equals 0. No, excuse me. 4B equals 0. Let me see, let me check because I don't want to make mistakes. It's correct. B equals 0. And this is 0 equals 0. Allow me this notation. We can see that everything is equal to 0, right? Because if B equals 0, I don't know if I made a mistake. Let me check. Did you see mistakes? No. This means if I don't see mistakes, if E equals 0 and B equals 0 is the solution. This means they are independent, right? Implies dimension of image of A equal to conclude. I need another slide. Excuse me. That's I forgot for this. Okay. Okay. This means in accordance to the theorem, dimension of image of A plus dimension of null of A equals dimension of V domain, we have 2 plus 1 equals 3. Now, I will ask you, is this transformation, think about, is the transformation surjective? Think about it. I can help you a little bit. There is an error in the slide. No? Yeah, there is an error in the slide, but what I did is correct. In your opinion, let me switch. Yeah, this is correct. In the slide, we have an error. We have the dimension, the image equal to, if I didn't make mistake here. Because we have two independent row. Yeah. But also the dimension of the codomain is 2. This means, is this transformation also surjective? Please pay attention. Is the transformation also surjective? In the slide is wrong, huh? It is. The transformation. I know what is the error, no, in the slide. Is surjective. Because in the slide is copied wrong the matrices, and now we will do exactly the example of the slide. I will improve the slide. No, I will improve the slide. I show you what I intend in the slide, but I made mistakes in the matrices. With the new matrices in the slide is correct. I mean, did you agree that the transformation is surjective? Yes, because the dimension of the image is equal to the dimension of the codomain. This means I don't leave, let me say, anything out. I cover everything. This is already clarified. Okay, in the slide, the result is correct if I consider instead of this matrix, this one. Think about this case. This is the case which gave the result in the slide because I forgot to put this in the slide. Please pay attention. I forgot to put this minus. Question. Now we take a rest, but the question is, and with this matrix is correct in the slide, but I will upload this for you. Is the transformation injective? First question. Questions. Is the transformation surjective? Okay, think about, we take a rest 15 minutes and then we will come back. Excuse me for the error, but I have a better presentation. Again, let me show you what is the error. I made mistakes in the sense is I copy. I mean, everything is correct. What is written here? Oh, also no. I have to consider not the beta transformation, not the beta presentation. Probably this was, I mean, I will look for because a little bit wrong. I will look for a better presentation because probably let me see. Yeah, I see some what I do in the manuscript is correct. What I do in the manuscript is correct. Please consider this, and then we will come back. We do together the solution. Consider this example here. Huh? Everything which I did today in the manuscript is correct. We take a little bit rest, 50 minutes, and then we will come back. Okay, let me restart with this exercise, which now is in my study. Please pay attention. I re-upload this exercise because in LaTeX I forgot this minus, and with this minus we have a totally different results, which is correct with the result. At least I did very quickly, which is correct the result with the new file which I uploaded, but was wrong because in LaTeX I forgot this minus. And then I correct another sentence. I show you very quickly because I realized that was not. Look, now I corrected in the example this minus. Now we will go through. It seems to me everything corrected. Now we will do together this example. Do you remember? Here was plus. The reason is LaTeX, you know, LaTeX probably sometimes it's not so easy to do. And then look, scrolling down, I realized also here, where is it? There is in the word not, yes, everything is correct. I mean, where is it? Yeah. M is number of independent row, which is the dimension of the image. We have a scene exactly now. And what was there? I forgot to cancel here times. Yeah, we can see here times. Now I will tell you a little bit more in depth about the rank. I don't remember what I correct here. But this slide now it seems to be everything correct. I mean, here, M is the number of row, is the dimension of the codomain. The number of independent row is the dimension of the range. As I told you, we don't have, it is not the same range in codomain because here we have the number of independent row. We have seen also the example. Here we have the number of the row. Here is now is correct. Probably before I copy independent from this in the LaTeX. The dimension of the domain is the number of columns, no? Not in the number of the independent column, because probably I copy from here to be a little bit quick. Now is everything correct? Excuse me for the error. I will clarify a little bit. I will go in depth on the concept of full rank column, full rank row. Okay, this is a little bit. This is a presentation a little bit better, no? Okay, let me do together with you this example, and then we will compare with the result which I have in my study. It seems to be correct. I forgot this minus, basically. Okay, think about these two questions. I give you 3 minutes to answer the first question, and the first question can be answered considering the kernel, for instance. The kernel must be the trivial kernel, just the element 0, 0. Excuse me, 0, 0, 0. The domain consists of 3 dimensions, dimension 3. And then please do this, try to answer the second question with the surjectivity using the independent or dependent concept of the row. And then we will see really in a rapid way, let me say, form to, let me say, answer in any case the second question. But why not also the first one, considering this dependent, independent row concept and rank of a matrix, In the meantime, I need just 1 minute to call. Try to do exactly what we did for the previous matrix. Try to do exactly what we did with the previous matrix. This matrix now is in my study, the new version of the of the presentation because I forgot this minus here. The rest, it seems to be correct. Now we verify, no? We verify. Okay, I do read. You have the solution? Injectivity. The rapid way for the injectivity is, of course, to check the independence number of row and so on. But I didn't tell you yet in depth. Let me do the calculation, then I will show you an idea or the method to say directly. But let me do the calculation. Kernel of A. Okay, kernel of A in accordance with the definition is this. The calculations are equals as before, equal in the sense conceptually. No? I mean, conceptually is the same. This means from here, x equal y minus z. If I plug in, let me use this notation in order to understand, in order to show you I plug in. It's clear what I intend. We consider this expression here into, yeah. 2 times z. This is true for each y, for each z. Did you agree? If I write 0 equals 0, I have to add nevertheless for each y, for each z, because in this equation, we have y and z. This is that. This means independently. Excuse me. Independently, what happens here for x, y? Let me say in this form. We have a 0 equals 0. This means independently for each y, for each z. I translate this independently. This means, look, this is the condition. At the end, I have this condition. What is this? Do you remember? I try to interpret now. You remember this? What is this? In 3 dimensions. What is this in 3 dimensions? It's the plane. Just to recall what we did in analytical geometry. It's in the plane. This means the kernel has 2 dimensions. Every point belongs to this plane, goes to the kernel. Now, if the kernel dimension 2, the domain dimension 3, what is the dimension of the image? 1. Because the dimension of the kernel plus the dimension of the image equal dimension of the domain. Please, in the first slide, we have the word independent, which is not correct. The dimension of the domain is the number of the column, punct, not of the number of independent column. It was an error in LaTeX copied. But the dimension of the image is the number of independent row. I will insist on this. I will insist a little bit. But formally, do you remember, we learned also in this form. For each y and z means that I can write the kernel in this quite abstract form. For each y and z. This came from my solution. I mean, the solution, please pay attention to this concept. The solution is this one and this one for each y and z. Both are the solution. At the end, we conclude this. I don't know if it's clear. The solution is this and this. What we say at the end. But this can be written in this form. I don't know if you remember, we did this exercise. Can be done, for instance, in this form. Let me write in this form. Again, don't forget, for each y and each z. What I have to write here? What I have to write here? 1 minus 1. What I have to write here? 1, 0, 0, 1. Look what I did. And important for y, for each y and each z, this remains. These 2 vectors, please pay attention, these 2 vectors are the generator of the plane. Do you remember this word? These 2 vectors are the generator of the plane. But at the end, in this context, in this exercise, what I have to know? What is the dimension of the kernel? There's 2. 1 dimension, second dimension. Now, from the nullity theorem, I know that the image of the transformation is dimension 1. Why that? Because dimension of the image plus dimension of the kernel equals dimension of the domain. Domain is 3, no? The number of columns, please, in the original, in the first slide, there is an error. I copied the independent word. The number of columns represent the number, the dimension of the domain. Now, if you look at the nullity theorem, we conclude directly, but dimension of domain, which is 3, equals dimension of kernel of A plus dimension of image of A. This is 2. This means this must be 1. But dimension of image of A is not equal the dimension of codomain. Because the dimension of codomain is the number of row. This means 2. And this is 1. This means the transformation is not surjective. But we can do also formally. How? A little bit more, with more calculations, in order to understand or to apply different concept. With minus here, no? Yeah. I made also the same mistake. This case is with minus here. Now we will see that not both elements are 0. But the solution is already here. No? We already calculate, or we came to the solution using the nullity theorem. But now more using another exercise. It is a little bit boring. From here we have alpha equal to beta. If alpha equal to beta, I transform here. We have minus 2 beta plus 2 beta equals 0. This means 0 equals 0. Please pay attention for each beta. Do you agree? When we have a 0 equals 0, we have to add for each beta, because here beta appears here. Otherwise, it's not consequent. 0 equals 0 is not a sentence. That doesn't say anything. Please pay attention. This is important concept in math. No? Where 0 equals 0 come from? From this condition. This means we have to add in the solution. I mean, the solution is not 0 equals 0. Please pay attention. 0 equals 0 is not a solution. A very important concept in math. 0 equals 0 is an identity. It's not the solution. The solution is 0 equals 0 for each beta. In German, there is an interesting sentence, Aussagekräfte. 0 = 0 is not Aussagekräfte. But if 0 = 0 for each beta, say something, I put in a condition. I mean, for each, you can put whatever you want. This is a condition in the sense you can put whatever beta. Really, here also whatever alpha. But it's very important beta to point out. Also beta, no? Because if for each beta, also alpha in this sense. Of course, also. And this means I can now directly say alpha if for each beta, this means also for each alpha, no? Because you can see here plus 2 beta minus 2 beta equals, at the end we have this as solution. Maybe 6, no, that's okay, no? No, I think I made mistakes. Let me see. This is okay. No, this seems to be right, no? 0. Again for each beta, no? Yeah, again for each beta, no? This means I don't need to have both, no? 0 zeros to obtain 0 0. This is exactly what I want to show. I don't need both 0 0. This is the condition. I write at the end of this. The condition this. But of course, I can, as I told you a little bit, I told you strange, I can write beta equals alpha divided 2 for each alpha. In the sense, the idea was to explain that could be also expressed in terms of each alpha, but this is enough one. This means not necessarily both 0 0. Very important, this transformation here for each beta, or, let me write, I did a little bit confusion, but now it's clear. No? For each alpha is equivalent, but in any case, not for both 0 0. This means they are depending. This implies that image of A equal 1, which is not equal, basically say dimension, excuse me, of the image of A equal 1, which is not equal dimension of the codomain. Now, at the end, we are able to do really this exercise in a very quick form. I show you how. I need another page. Because now, thank you, thank you, thank you. we can say if the matrix is not full row rank, the system is not surjective. I write for you. If the matrix is not full row rank, the transformation is not surjective because the domain of the image is not equal to the domain of the codomain. I write this sentence for you. Then we can directly know the solution. Look at the matrix. If the matrix is not full color rank, the matrix is not injective. I'll show you with this. Because we have something that is going in something not zero, the dimension not zero, which is going in the kernel. I'll show you now more in detail. If the matrix is not full rank means is neither full column rank nor full row rank, it's not injective, it's not surjective. I show you everything now. As a scheme, in order, if I give you a matrix, you know immediately if this matrix represents injective or not injective. Let me draw this scheme for you. If a matrix is full row rank, this means full row rank means that all rows are independent, right? Although a little bit strange. Independent row is better, no? But independent row. This implies dimension of image of matrix M equals dimension of codomain. This implies surjectivity. Or viceversa. If the surjectivity implies this way. This means if it's not full color rank, it's not surjectivity, not subjective. We don't have a subjectivity because it's in a theory in both directions. Look at the slide. You can find this. Look at the slide. You can find it. If a matrix is full column rank, independent column, this implies kernel of the matrix, or the better to say dimension of kernel of matrix equals zero. This means just a zero in inside. No? This implies injectivity. And vice versa. The theorem was if and only if. If we don't have the full color rank and we don't have the full row rank, it's not injective, it's not surjective. I draw for you. full column and we don't have imply no injectivity, no surjectivity. Both is not satisfied. Of course, if both are satisfied, we have it. In this case, no full column and no full row rank, we say that the matrix is not full rank. If you lose both, no? But for each matrix, please pay attention. Rank, as you can see in the slide, rank of column equals rank of row. It's very important. For each matrix.
But you repeat the.
Yeah, I do everything with also other exercise. I repeat this sentence here.
I know the third statement.
This one.
Yeah.
If you don't have a full color rank and we don't have a full row rank, both and not guaranteed, no injectivity, no subjectivity. Of course, I didn't wrote if both are guaranteed, we have both, injectivity, subjectivity. Now, don't learn this. With example, we repeat it we automatically, believe me, without do this test, almost without do this test of the kernel and also linear combination. Copy in any case, because a good scheme, you can find then in the corrected, I mean, this was correct, in the corrected version of the slide in my study, but believe me, we don't need. Now we will proceed intuitively. Copy, it could be nice, and then look at the exam exercise. A equal. Copy in the meantime, no? If the corresponding transformation injective, subjective, corresponding means, if you remember, no, we can associate the matrix and transformation. Please look at me and we will discuss everything which I wrote here with the example. So it will be automatically. Look, for each matrix, rank of column equal rank of row. Isn't it theorem? I don't have time to show you now. Look, what is the possible maximal rank in this matrix? What is the possible maximum rank? 2. Because if the rank of column equals the rank of row in each matrix, cannot be more than 2. Because assuming that the 2 rows are independent, I didn't verify, but assuming that the maximum possible is 2. This means we know already something about the injectivity. Is it injective or not? Is it injective or not? We know already, we can answer directly.
No.
Correct. We don't need to calculate the kernel, but I'm not so nice in the exam. I will impose to calculate the kernel, but you know there is something in advance. This means it's impossible to make a mistake. We know that the dimension of the kernel cannot be trivial, just the element C. Must be a dimension. Why that? Because the maximal rank is 2, could be also 1, but in both cases, the column are depending. This means there is something which is transformed into 0, something which is not just 0, it's a dimension. It's an advantage to know the result. Always, I do this example, I do this exercise because in application of math, very often we have to guess the solution. We have to have an idea about the solution. Yes, clear the solution. And then we demonstrate what the solution is. Of course, in this case, we don't need, but didactically, it's important to understand how a mathematician works. Mathematician try to, in this case, we have a theory which helps us, but try to go in advance the solution. Or at most, in this case, it's clear that the solution or the transformation, the corresponding transformation is not injected. A trick. This message. Look at me. A trick. So the long horizontal matrix is always not injected. Let me speak about the filling, in which we have more column than row. This is in the slide. In the slide, we have on the slide, very difficult to be interpreted because it's mathematically expressed. But look at me. A long matrix with more column than row is always not injective. Look, in this today, I put also some theorems in which we say the number n larger than m, if you look in the presentation, is not injective. Try at home to do the kernel of this matrix here. But we did 3, 4 times. It's easy. Now, before going, what about the injectivity? The injectivity, then try to calculate the kernel, because in the exam I want that you calculate the kernel, because a mathematician works exactly so, intuition, or we have a result from a different let me say knowledge, and then we demonstrate or we show in another form. What about the subjectivity? In your opinion, it's easy. Think about the nullity theorem. It's directly the answer. The nullity theorem, which I will put in the data sheet, the form example. Avoid doing calculation, but in the exam I would like to do the calculation. But you know the solution. It's impossible to make mistakes. When you know the solution or you guess the solution, in this case you know. If you guess, it's a bit more difficult. Guess means in your camp solution. But here you have. It's just to demonstrate in another form. Nullity theorem. What says the nullity theorem? Says the dimension of the domain. What is the dimension of the domain? Because it's the number of columns. Please pay attention. In the first presentation is written independent, but I cancel because in an error in LaTeX. A few minutes we conclude, because me too am totally. We had a day with these seminars. Yeah, 3. Did you agree? The number of not the number of independent. Because the number of independent is maximum 2. Maximum. We don't know how much, but maximum 2. The number of columns is 3. This is the theory, which states the dimension of the domain. Equals what? the dimension of image plus the dimension of the kernel. It's difficult to remember this. No, it's not difficult. Because what I transform from the domain, let me say, what goes to the kernel, plus in something goes to the kernel, could be also just the element 0, and the rest get to the image. What is not annihilated will be projected, but the projection is the image. Now, 3 equal what? Dimension of the image plus something which is not 0. What do you think? It depends on the dimension of the kernel. The dimension of the kernel is not 0. This means the dimension of the kernel could be 1 or it could be 2. Now, if the dimension of the kernel is 1, we have the surjectivity. Because we have the dimension of the image equal to, which is equals the dimension of the codomain. Because the dimension of the codomain is the number of row. The dimension of the image is the number of independent row. We have this difference between image and codomain, or dimension of the codomain, or difference between the image and codomain. In your opinion, without do the calculations, we don't want to do the calculation of kernel. In the exam, you have to do. What is the dimension of the kernel? Or better to say, what is the dimension of the image? Or it's probably easy to see, what is the dimension of the number of independent columns? Or if you like, what is the dimension of independent row? Is this a row independent of this? Yes, because we have a 0, we have a 1. I mean, look at the row, the column if you want. This column here, depending on these two, because this plus this equal this. But these two columns is totally independent because we have 1 here, 0 here, 0 here, 1 here. They are orthogonal. Of course, this method here works if we have a few, but if the big matrix, we have to calculate the kernel, and then we apply the nullity theorem. Dimension of V equals dimension of image plus dimension of kernel. This means the dimension of image equal dimension of V minus dimension of kernel. If this is not equal to the dimension of the codomain, is not. The transformation is not a surjective one. Huh? I mean, it's surjective if the dimension of image equal to, this means if two rows are independent. If it's not the case, it's not surjective. Okay, try to do at home. Next week at the beginning, we do this exercise together with this. But now, look, in a vertical matrix, this means injective, because the number of row is larger than the number of column. And look at home about the surjectivity, but we can see, because of this reason, we have that the row rank is not full. If you look at the scheme here, we don't have the surjectivity. Again, here we don't have the injectivity, but we have the surjectivity because this row, the rows are independent. Here we have the injectivity because the columns are independent. But because of the no full row rank, we lose the surjectivity. If no full row rank, no full column rank, it was this case here, we lose both. No? You remember here? No surjectivity. No surjectivity. In the case we calculate, and no injectivity. Where is? We did, no, nevertheless, somewhere. We calculated the kernel here, no? Yeah, exactly. Yeah, no injectivity. I didn't write, but it's no injectivity. Why that? Because this matrix is not full rank. Ready, is not full rank. No full column rank, no row column rank. Next week, one block, we go ahead a little bit here. Thank you for your attention. Two blocks, next week. Wait for me here. No? Ciao. Okay. Thank you for your attention. We will see you next week.